Welcome back, AP Stat. We're going to be talking about a couple things to set the stage for Chapter 18, the first of which is the topic of point estimates. What is a point estimate? So on page 471 of your textbook, we see that researchers find that 51.9% of a sample of 104 sea fans in Las Redes Reef off the coast of Mexico have a particular disease. Suppose we wanted to estimate P. P is the population proportion of all sea fans that are diseased. A decent guess would be 51.9%, but that is likely not the right answer. This 51.9% is an example of a point estimate. It's a one-number estimate of a parameter. With our information, it's the best we got. We'd say that the best point estimate for the population proportion is the sample proportion. The population proportion is unknowable. There's no way we're going to be able to research all the sea fans in the world. There's so many of them. But with the 104 that we have, as long as it's a good sample, we can estimate the population proportion using our sample proportion. Other examples of point estimates are X bar, that approximates the population mean mu, and S, that's the sample standard deviation, which approximates the population standard deviation. Now we need to talk about biased and unbiased estimators. What is a biased estimator and what is an unbiased estimator? So suppose we took many samples of the sea fans and plotted a sampling distribution of the sample proportion of infected sea fans, and that those samples formed a bell curve centered at 51.5%. Suppose the true proportion of infected sea fans is actually 50.1%. Now, to be clear, we're referring to this fella to the left over here, this distribution. We have a bell curve centered at 51.5%, but this bold arrow points to what the true population proportion is. If the plot of our sampling distribution looked like the plot to the left, which I just pointed to, then we'd say our sample proportion is a biased estimator of the population proportion. That's not necessarily a bad thing. A biased estimator is often the result of bad sampling. We may have sampled from parts of a coral reef that were particularly unhealthy to get this distribution. However, a biased estimator may cause us to consider whether the assumed proportion of infected sea fans is actually incorrect. Suppose we were given, in a textbook, in a manual, in prior research, that the proportion of infected sea fans is 50.1%. We assume that's the population proportion. But then we do some research, and our research methods are good, and we find that the proportion that the bell curve is centered on is actually that. Well, that could mean that this number has an issue, and maybe it's a bit outdated. So biased estimators are not a bad thing necessarily, but they are often due to just bad sampling. However, if we actually got a p-hat value of 50.1%, like we do in this distribution over here, the sampling distribution resembles the plot to the right, and p-hat is said to be an unbiased estimator of p. The sample proportion is exactly where we expected it to be all along. Hence, it is unbiased. An estimator, like p-hat, is said to be unbiased if the expected value, that's the same as the mean, of the sampling distribution is equal to its corresponding parameter, like p. Otherwise, the estimator is said to be biased. The greater the discrepancy, the greater the bias. So the further we are from the assumed population mean, the further our distribution curve is centered away from the assumed population mean, the more the bias. And again, bias is not necessarily a bad thing. It might mean that the assumed population parameter is outdated. Nonetheless, it is nice to see the sample proportion be an unbiased estimator of the population proportion. It is nice when our research gives us a sample proportion that is essentially the same as our expected population proportion. Oftentimes, that means we are on the right track.